Hello, this is Lab 2 for Physics 2211. Let's jump into it. So a quick introduction. The purpose of the lab is to identify how gravity and friction affect falling objects, and the initial conditions of the object are that it begins at rest with a velocity of 0 meters per second. So call back to Lab 1. Although the axis changed from horizontal movement in the x direction to the vertical movement in y direction for this lab, we still have to apply Newton's second law of motion, which is right here. But two new conditions for this lab are gravity and drag. Gravity is defined by this equation where the force of gravity is equals the gravitational constant times the first mass times the second mass over the radius square. And for the terms of Earth, we can figure that out with the gravitational constant, the mass of Earth, and its radius square, which come down to be 9.8 meters per second squared. And so the force of drag, on the other hand, can be identified with this equation, where B in our terms will be determined through trial and error. And so for the physical experiment, I just dropped a ball from a given height, from a random height I should say, and then just plotted everything here. You can see the data. As the object falls, the velocity generally increases. Oh yeah. And so here's the first computation. Given gravity on Earth that we previously talked about, 9.8 meters per second, the time that it took the object to fall to the ground, 52.52 seconds, and then the change in the object's vector can be found with this equation, where in the y direction the ball's mass multiplies times the gravitational constant, or the gravitation here on Earth, and then the object's position is just found using the position update formula, where the final position equals the initial position times the ball's velocity and times the change in time. And so here are the two main numbers that we needed for the equations. The time, 0.52 seconds, final minus start, and then the gravity here on Earth, 9.8 meters per second. And so here's the computational view for the first model, and how it compares to the physical experiment. For the first model, we can notice how there's a big change at the beginning and at the end with the physical model. The physical model tends to fall a lot faster at the beginning, but then slows down a little in comparison to the computational view. This is mainly due to the fact that we didn't account for gravity in the computational model, which tends to slow down the effect of gravity in the y direction. And so here we compute that now. Here's the constant for drag that we just again found through trial and error for this example, and then the updated net force, which now gets our initial y vector adds up to the equation that we've previously identified for drag. So here's the updated model, and this in the orange is the data for the second computational model, and here we see that it now ends off at the same point as the physical experiment, but we still notice that it's a lot higher than the physical experiment. This could be due to a slightly applied force when the object was dropped that the computational model doesn't account for. So what does it mean? The only model that could truly represent terminal velocity is the last computational model with drag, since it applies all the forces that could be applied on the object, drag and gravity, the most accurately. And then if the forces of drag and gravity balance out, then the object will reach a constant net force of 0.00 meters per second. And so the velocity would thus remain constant in the downward direction. Here you can see how the force of gravity continues to push it down, but is counteracted by an equal force of drag, which means that the velocity would remain constant. And so what if the object's does not begin at rest, well, one of two things will happen. If the object's initial velocity is less than the terminal velocity, then it will speed up, similar to how it did for the computational models, but it will reach the terminal velocity a lot faster. And if the initial velocity is greater, however, then it will slow. The drag force would be greater as well, and it would slow it down until it reaches terminal velocity. Thank you.